GCSE Computer Science, Syllabus Statement 1.3.4a. Describe the principles of operation of inkjet printers and describe how they are applied to real-life scenarios. So, finally moved on to output devices, but this really isn't going to be any different from what we did in input devices, except these devices output, and that's it. Yeah, it's the same format. Each video equals one output device, and that's it. So, an inkjet printer is a printer in which the characters or images are formed by minute jets of ink. This is the definition I got from the dictionary. One inkjet printer would look like this. Mine doesn't look too different from this, actually, but yeah. So we'll just be looking at how it works and how they are applied to real-life scenarios, just like we did with the input devices. So the components of an inkjet printer include a print head consisting of nozzles which spray ink droplets on paper to form characters or images. Ink cartridges, usually two, one black, one blue, one black and one blue, yellow, and magenta. But they can also come in other forms, such as one cartridge with all 4 colors, or sometimes cartridges with 6 colors. A stepper motor and belt, which moves the print head across the paper. And a paper feed, which feeds the printer with paper. So, using all these terms, we can now go on to see how the inkjet printer actually works. So, there are 2 technologies of the inkjet printer. There's thermal bubble. In thermal bubble, tiny resistors create heat, making the ink vaporize. The ink forms a tiny bubble, which expands, causing some of the ink to land on the paper from the print head. The bubble collapses, and a small vacuum is created, allowing new ink to be drawn into the print head. This continues until the print job is complete. And then there's piezoelectric. I'm guessing that's how you pronounce it. Piezoelectric. Anyway, a crystal is located at the back of the ink supply for each nozzle, and it's given a tiny electric charge, which causes it to vibrate. The vibration causes ink to land on the paper from the print head. And while this is happening, more ink is drawn in for the next print. So whatever technology is chosen, I think it's usually thermal bubble. Both technologies follow this basic algorithm when printing. So, first step is data from the file to be printed is sent to a printer driver. This can be from a computer. The printer driver checks that the data is in an understandable format. The printer driver checks if the printer is able to carry out the print job. So, what this basically means is it checks if the printer is, checks the printer, if it's busy, or if there's a paper jam, or if there's no ink, or some other error, it'll send a message back. So the data is sent to the printer if there are no problems, and the data is stored in a printer buffer. Now, we'll learn about buffers soon, but just know that a buffer is sort of a temporary memory location. Next, a piece of paper is fed into the printer. If an error occurs, a message is of course sent to the computer. Now, error message could be, out of paper, or something like that. Anyway, the printer head moves across the paper to produce the characters or images. At the end of each pass of the printer head, it doesn't matter what you use, honestly. I just did this to, actually I didn't really do it for a purpose, anyway. So the paper is advanced slightly to print the next line. The process from step 5 is repeated until the printer buffer is empty. And finally, the printer buffer sends an interrupt to the computer. An interrupt is, just for now, think of it as a signal, because that's pretty much what it is, but we'll learn more about it soon. So an interrupt is sent to the computer requesting more data to be sent. So that's pretty much the algorithm of an inkjet printer when it's doing a job. So this is what an inkjet printer looks like on the inside. And as you can see from this image, it's most probably thermal bubble, because you can see the bubble, the growing, expanding bubble. So you can see the ink cartridges here, the stepper motor, the print head, the paper, and the belt. And that's pretty much how it works. So the use of inkjet printer, well, inkjet printers are best for printing good quality one-off photos. So like, when we learn about laser printers, we can start to distinguish between inkjet and laser. So basically, yeah, it's good for good quality one-off photos. So like only a few pages, as opposed to large print jobs, which laser printers are best at carrying out. And this is because the ink cartridges are quite small in inkjet printers, and so are the paper trays. So there's less likely to be issues. Well, not that there would be no issue. Well, I mean, there could be issues, but yeah. So it's basically good for like one-off photos, like really small files, really small print jobs rather. Hi, GCSE Computer Science. Syllabus Statement 1.3.4b. Describe the print... Yeah, you're probably getting bored of me saying this. Anyway, laser printers... well, a laser printer is a printer which makes use of powdered ink and static electricity to carry out print jobs. So laser printer kind of looks like this, but they tend to look a bit bigger, actually. Yeah, and they usually have larger trays than this. Anyway, laser printers, as said, use dry powdered ink instead of liquid ink to print, like inkjet printers do. They also use static electricity to print characters and images. Unlike inkjet printers, which print line by line, laser printers print the whole page in one go. Whoa. Pretty cool. This gives them a speed advantage, which is why they are suitable for large print jobs. You may see inkjet printers if, like in your school, for example, or wherever you are, and you'll notice if you've used them that they're pretty damn fast. So yeah. They also don't run out of ink halfway like inkjet printers do. So you may notice if you print with inkjet printers, the ink may tend to run out halfway, and it's kind of annoying. But laser printers, it's a lot less likely. Anyway, here's the algorithm. So the data from the files to be printed is sent to the printer driver. Yes, printer driver checks the data is in an understandable format. And I'm rushing through these because we looked at this, like these steps in inkjet printers, but it's a bit different once we get to a certain step. The printer driver checks if the printer is able to carry out the print job, so like checks the printer, it's busy, no paper, whatever. The data is sent to the printer and stored in the printer buffer. But here we go. A printing drum in the printer is given a positive charge. Now, you might be wondering, what the hell is a printing drum? Well, a printing drum, you're going to find out what you're going to see what it looks like, but just know that a printing drum is kind of like something that rolls. You'll see in a minute. So it's given a positive charge, and a laser beam removes positive charge in certain areas on the drum. This, of course, leaves negatively charged areas, which match the characters or images to be printed, which is pretty cool. The drum is then covered with positively charged toner, or powdered ink, which sticks to the negatively charged areas of the drum. So that's how it happens. A negatively charged piece of paper is then rolled over the drum, causing the toner to stick to the paper. The negative charge is removed from the paper to prevent it from sticking to the drum. And finally, the paper goes through a fuser, which melts the ink onto the paper, and a discharge lamp removes all the charge from the drum to prepare it for the next job. So that's pretty much how it happens. If this is unclear, we're about to see a picture, so maybe you'll get a better idea. That's a bit just sort of threw stuff there, but if you get it, good. If you don't, well, take a look at this. So here's the paper tray. The paper gets rolled. Here's the drums, as if you were wondering what it looked like. It's kind of like a big rolling pin kind of thing, I guess. So here's the toner hopper, like the place where the powdered ink is stored. So then there's the laser. The paper is then sort of, yeah, you can see, pushed through, and then the fuser, which melts the ink, and then finally it exits. And the discharge lamp is somewhere over here. So yeah, that's pretty much how it looks. If you were wondering, it kind of looks like that. So you can hopefully get a better idea of how the printer works. So here's the use of laser printers. Now in the last video I said they're good for carrying out large printing jobs, which is true. Because as mentioned, laser printers have a speed advantage over inkjet printers. So laser printers are good for large, high-quality print jobs. So in other words, high-volume printing. So an example is printing many flyers or posters to put around the town, or printing a lot of exam papers for students who are taking their IGCSEs. So yeah, that's an example of when it would be good to use a laser printer over an inkjet printer, because an inkjet printer would honestly take hours to print like a lot of posters. And another reason for this is they have large toner cartridges and large print trays, which also gives it an advantage because you don't have to keep putting paper in the tray, you don't have to keep changing the cartridge. So that's about it. IGCSE Computer Science, Syllabus Statement 1.3.4c, and this video is 3D printers. So a 3D printer is quite a bit different from laser or inkjet printers, because instead of printing onto paper, they print objects. So this is the definition. So yeah, a digital object can be printed or produced. It's usually used in computer-aided design. Now when we looked at 3D scanners, we looked at computer-aided design with them. So what you could do is get a 3D scanner, scan an object, put it on your computer, and then print the object on the 3D printer from your computer. So there's that. That's pretty cool. So yeah, a 3D printer kind of looks like this. So there's a little city there. Anyway, there are two types of manufacturing for 3D printers. One is additive manufacturing, where the 3D object being printed is built up layer by layer using powdered resin, powdered metal, ceramic powder, or paper. So it's quite a lot of powder. Another type of manufacturing is subtractive manufacturing, where 3D object being printed is carved from a block of stone until the object is formed. Now this type of manufacturing for 3D printers is less common than the additive manufacturing because, well, we could use powdered resin, powdered metal, and quite a lot of other materials. So basically a more diverse amount of, you get the point. Like, you could use more materials for additive manufacturing than subtractive, because subtractive is just like one material where you carve it. It's kind of yeah. So then there's types of technology which 3D printers use. One type is direct printing. This uses inkjet technology. So a printhead moves side to side like an inkjet printer, but can also move up and down to build the layers. So you can imagine a printhead which can ground XYZ coordinates as opposed to X coordinates like 2D inkjet printers. Like inkjet print heads can only move left to right, side to side. 3D printers can move up, down, left, right, whatever. Another type of technology 3D printers use is binder printing. So the print head moves like in direct 3D printing, but two substances are sprayed for each layer. So there's the dry powder and the binder, which is a type of glue to form the object. And there are also some other technologies which make use of UV light to harden liquid polymers, and this increases the diversity of products that can be produced. You don't need to know much about that, just know that there are other technologies and UV light. Yeah. So here are the steps involved in 3D printing. So a design is made using computer-aided design software on a computer. The design is imported into software which converts the design into an understandable format for the 3D printer to read. The 3D printer is set up to print the object. The object is built up layer by layer. The layers are usually 0.1 millimeters. But this step can take hours, of course depending on the thickness of the layers and the size of the object being printed. So if you imagine how slow an inkjet printer is, here's a 3D printer. And finally, once the print job is complete, the object is finalized, depending on the object being printed. Now when we say finalized, we kind of mean finished off. So like excess material removed, like cutting unused material from the object, like basically finishing it off to make it look better. This can take quite a while as well. So finally we get to the uses of 3D printers. Now, if you noticed, in inkjet printers and laser printers, I just said use. Well, we see uses here, which means that 3D printers have quite a lot of uses, even though most people don't really use them, unless you're watching this in 2030, and then, like, 3D printers are like, the thing. Anyway, so use of 3D printing is to make prosthetic limbs for patients. So it's basically if a patient, like in war, loses their arm, then or like one of their joints or whatever, then a 3D printer can print it. Now, you can imagine it kind of like building up the design in CAD software and then printing it. So you can be pretty accurate with this. Or you could use a 3D scanner to scan some of their other limbs to see how it, quite a few things. You can also make items which allow precise reconstructive surgery. So it's kind of similar to that, but basically, if you need to reconstruct someone's, say, face, then you can be really precise with what you print in order to put it on the person's face. You can also make lightweight plane wings. Now, this is a bit risky, but with time, hopefully people can actually do this, because, it's much easier than having to build up wings stuff. So, yeah, it's quite cool. Making sculptures, so like, this doesn't really require an explanation here. We're making sculptures, so like art sculptures, models, and also making items which are no longer produced in industry. Now, I think this is especially important, and this is because if you're watching this now and you're like 70, well, you might realize that some of the stuff that you had back then isn't produced anymore now. So with 3D printing, you can design it and then print it. So yeah, that's pretty much it. IGCSE Computer Science Syllabus Statement 1.3.4D. Describe the principles of operation of 2D and 3D laser cutters, and describe how they are applied to real-life scenarios. I just realized that some videos, when we say we're going to describe how they are applied to real-life scenarios, we actually don't really describe how they are applied to real-life scenarios. But, we kind of do to an extent. Right? Because, like, some devices we can actually do in, like, it's kind of, never mind. Alright, so I'm sure that people can just apply them to real life scenarios. They can think of something So yeah, we do talk about it to an extent. So laser cutters. So a laser cutter is a device which can cut materials. That's pretty self-explanatory. So a laser cutter can cut materials such as glass, polymer, metal, crystal, and wood. And some guy's shouting outside of my house. It's kind of annoying. A 2D laser cutter cuts in the XY direction, while a 3D laser cutter cuts in the XYZ direction. So, again, it's pretty self-explanatory. So, like, you can think of a 2D graph, XY, 3D graph, XYZ. So it has the third dimension. The laser cutters are controlled by computers, and this allows complex and cool designs to be made. So that's pretty much it for cutters, really. I mean, I guess you just have to know about the materials and how they're controlled, really. But this is what you can create with them. This is a cool rhino, as you could see. It's really quite detailed, so yeah, it's cool. IGCSE Computer Science, Syllabus Statement 1.3.4e, and this is actuators. So in this video, we're actually going to see how they are applied to real-life scenarios. But anyway, if you remember from our the sensors video, we looked at microprocessors, sensors, analog to digital converters, digital to analog converters, and then we looked at actuators. So what is an actuator? Well, an actuator is an electromechanical device used to operate or control something. And they kind of look like this. So this is a motor, and this is a valve. So, yeah, that's pretty much it. So an actuator, such as a motor, relay, or solenoid, is used in a controlling application. And when it's energized, an actuator can operate or control a system. So like a solenoid could be used to operate a plunger or control a fuel injection system. And a digital to analog converter is sometimes required to control an actuator. So a computer or microprocessor is connected with the actuator, and data sent to it will go through the digital to analog converter when being transmitted to the actuator. So we can remember from what we... Yeah, this guy is really going at it outside. Anyway, so we looked at sensors. So we looked at how the sensor sends signals to the microprocessor through an ADC if required. The microprocessor checks the sent values against stored values, and if something happens or if the value is out of range, then it can then send a signal to an actuator, so like a motor, for example, through a DAC to make it do something. So that's pretty much how actuators are used. IGCSE Computer Science, Syllabus Statement 1.3.4f, describe the principles of operation of speakers. And, yeah, speakers. There aren't as many output devices as there are input devices, I think. I'm not entirely sure about that, but I know that the output devices videos will tend to be quite short compared to input. Actually, I have no idea. But anyway, so a speaker is a device that converts electrical impulses into sound. And when we say speakers, we mean loudspeakers or headphones. So anything that speaks or outputs sound. So sound is produced from a computer by transmitting digital values through a DAC, and then through an amplifier, and finally to the speaker, where it is output. So here's the computer. Digital data goes to the DAC, analog data comes out, amplifier, amplified data goes to the speaker, and this outputs the amplified data. So the rate that the DAC can convert the digital data into analog voltages is known as the sampling rate. If the DAC is 16-bit, it can accept 2 to the power of 16 numbers. So that's 65,536. So that would be negative 32,768 to positive 32,767. So that range is 65,536 values. including the 0, of course. The speed that these values can be converted is the sampling rate. The typical sampling rate is 44,100 Hertz, or samples per second. This means that the DAC is able to convert 44,100 values every second. So let's look at an example. A CD is being produced to hold a number of music files. Each music file will be sampled 44,100 times per second, each sample being 16 bits. We must also take into consideration the music being stereophonic, or stereo. Taking the above into account, we can calculate how many bits per second can be sampled to the CD. So we have 44,100 times 16 times 2. Well, where does the 2 come from? Well, we say that it's stereophonic, so that's where the 2 comes from. So that would give that many bits per second, and 8 bits is 1 byte. And so we just divide that by 8, and we get 176,400 bytes per second. IGCSE Computer Science, Syllabus Statement 1.3.4G, and this video is about monitors. So we're going to be looking at two different technologies. We're going to be looking at, we're mainly going to be looking at LCD and LED, as well as OLED, but we'll also compare the LED to the CCFL and the OLED to the LED. That'll all make sense soon enough, but anyway. A monitor is a screen which displays an image generated by a computer. So this can mean like the screen right in front of you, or the TV in your living room or bedroom, or your smartphone. So anything that generates an image. So it can look like this. So most monitors and TVs nowadays use LCD, or liquid crystal display technology. And in LCDs, the front layer of the screen is made up of liquid crystal diodes. And these diodes are grouped in 3s or 4s, and these are known as pixels. The groups of 3s are made up of red, green, and blue. The groups of 4 are made up of red, green, blue, and yellow. And the yellow makes the colors look more vivid. Modern LCD monitors are backlit using LED, or light-emitting diode technology, which is designed to give the image better contrast and brightness. Back then, LCDs used CCFL technology as the backlighting method. So this is what I was talking about. So we're going to be comparing LED and CCFL, and then when we move on to OLED, then we compare that with LED. It's kind of weird, but whatever. What CCFLs use are two fluorescent tubes behind the LCD screen. But LEDs use a matrix of tiny LEDs, or light-emitting diodes, behind the LCD screen. This, I know when you read it, it kind of doesn't make sense, but I meant LED as in LED technology. Uses, it's pretty much. Anyway, here are some advantages of the LEDs over the old CCFLs. So LEDs reach their maximum brightness faster. That's quite helpful, because you don't want to wait for the maximum brightness to... my grandfather has an old CCFL TV, well, did actually. He doesn't live in his house anymore. He lives in a retirement home. But anyway, it was pretty bulky, and it was kind of annoying to have to wait for it to reach its maximum brightness. LEDs produce a whiter light, and it sharpens the image, making the colors look more vivid. And again, old CCFLs kind of look a bit grainy. LEDs produce a brighter light, improving color definition. LEDs last much longer, making their use more reliable, although I think the TV that my grandfather has still works. LEDs use less energy, which means that they produce less heat. And monitors which use LED technology, again, are much thinner than those which use CCFL technology. And now we get to OLED, or OLED, or Organic Light Emitting Diode technology. So this is an advancement of LED technology, which is a lot better than CCFL. So we're seeing like a lot of advancements here, and it's quite cool. So OLEDs use organic materials made up of carbon compounds to create flexible semiconductors. Organic films are placed in between two charged electrodes, which include a metallic cathode and a glass anode. And when an electric field is applied to the electrodes, they emit light. And this means that no backlighting is required, allowing for very thin screens. Actually, before we continue, has anyone ever seen like one of those really like those curved TVs in the shopping mall, or if you have one at home? Well, we'll get to that once we go here. So, OLED is a self-contained system, which means that there's no need for LCD technology. And as I was just about to say, OLED allows screens to be curved since they are flexible, and this ensures a good picture from any angle. So that's what I was trying to say. And due to its flexibility and thinness, OLED screens can be bent into any shape. And if this is applied to mobile phones, you can fold your phone and put it in your pocket or wrap it around your wrist. It's quite cool. Like imagine if you have like this really, really thin phone. You just fold it, put it in your pocket. Like, I mean, you could put phones in your pocket now, yeah, sure, but like, I'll think of something bigger, like a tablet, like an iPad. So you just fold it, put it in your pocket. Or like a really big TV, just fold it. Like, it's quite cool. Like if like this, we should see a lot of this in the future, hopefully. So there are advantages of OLEDs over LCD/LEDs because these two work together. So OLED screens are thinner, lighter, and more flexible. OLED layers can be made of plastic rather than glass, which means that they can be made into large, thin sheets. OLEDs give a brighter light, yes. When we said that LEDs are quite bright compared to CCFLs, OLEDs give a brighter light. OLEDs, I'm just going to say OLED, it's better than OLED. I kind of alternate. OLEDs don't require any backlighting because they generate their own light, and this of course means that they consume less energy. And OLEDs have a large field of view, around 170 degrees, making them ideal for TVs and advertising. So yeah, all in all, a pretty cool topic. Yeah, I think this is my favorite output device because it's just cool to think about how like we could see like foldable TVs/phones/tablets/whatever. It's like, it's really cool. You could also do a lot more if you think like try to think of a lot of things you could do with this technology. Like you could, I don't know, like put it on your clothing and like make it look really cool. Yeah, I don't know. I don't know if you're thinking what I'm thinking, but anyway, it's cool. It's a cool technology, and we should see a lot more of this in the future, hopefully. IGCSE Computer Science, and this is the final output device that we need to know. This is projectors. So, in case you don't know what a projector is, it's a device that displays computer output onto a wall, large screen, or even in interactive whiteboard. So we usually see these in like meeting rooms and classrooms as well. So like if you remember what we looked at when we looked at interactive whiteboards and how they're quite big, so a lot of people can actually see what's displayed. Well, this is how like the computer is, well, the computer screen is displayed. It uses a projector, and if the projector and interactive whiteboard work together, then they can do some cool things. Now, I know that this might seem quite old because, you know, projectors came out a few years ago, but nah, you still have to know about it. They kind of look like this, although they can look a bit different. Some go on walls as well, so yeah. So projectors are usually used in presentations and multimedia applications. And there are two common types of projectors that we're going to look at. There's the digital light projector and the LCD projector. So yeah, let's jump into this. So DLPs use millions of micromirrors on a chip. The number of micromirrors and the way they are arranged determines the resolution of the image projected. So when the micromirrors are tilted towards the light source, they are on. When they are tilted away from the light source, they are off. The micromirrors can be switched on or off thousands of times a second to create various shades of gray. Anyone? No. The typical number of gray shades... Actually, I haven't seen 50 Shades of Grey. The typical number of gray shades which can be produced is 1024. So, let's look at an example. If, well, we're not really looking at the example. I'm telling you the example. You're kind of looking at the text. But if the mirror turns on more times than it turns off, a lighter shade of gray will be produced. A bright white light source from a xenon light, for example, passes through a color filter on its way to the DLP chip. The light is then split into three primary colors: red, green, and blue. And the on and off states of the mirrors are linked with the three colors to produce the colored image. Over 16 million different colors can be produced. So that was DLP projectors. Let's look at LCD projectors, which isn't that much. In fact, this video is, as you notice, is pretty short. So LCD projectors, let's look at how they work. So step 1, a beam of white light is generated from a bulb or LED in the projector. The beam is sent to a group of chromatic coated mirrors, which reflect the light back at different wavelengths corresponding to red, green, and blue light components. These colored light components pass through three LED screens, or LCD screens rather, not LED screens, and a red, green, and blue version of the gray image emerges. And finally, these are combined using a type of prism to produce an image consisting of millions of colors. This image is then passed through the projector lens onto a wall, screen, or interactive whiteboard. And that's pretty much it. Well, LCDs are a little bit older than DLPs, and they don't have the mirrors which turn on and off. They have these mirrors which reflect the light back at different wavelengths. So, yeah, it's pretty much that's how it works. I don't know what else to say. Actually, I do know what to say now. This is finally we're finished with devices. We're finished with input and output devices. Well, I wouldn't say we're finished with devices because we have memory and storage, and we have to look at a few more devices, but it's not that much. So off the top of my head, it's just RAM, ROM. Then magnetic storage, optical storage, solid state storage, and file sizes again. But yeah, it's pretty much it. Thanks for watching, people, and yeah.